All right. Thank you, everyone, for joining the Trees Around the Globe Student Research Campaign webinar. Today is Tuesday, March 17th, 2020. And today we're going to have a feature presentation. It's the title shouldn't scare you. We're a NASA agent. We're a science agency. But this is going to be an amazing discussion from Dr. Latha Bhaskaran. It's called the use of LIDAR. And LIDAR, if you don't know what it is yet, think about it. It's something to do with lasers, all right? The use of LIDAR to derive tree heights and other structural vegetation characteristics. Applications for mapping habitats in a post-fire environment. So, as you know, this is a Trees Around the Globe student research campaign, so we talk all things trees. But then I should also mention that, as you may know, we talk about land cover, we talk about carbon cycle, we talk about greenings, green up, green down, and lots of other things. But our focus is trees and our trees and tree height. So I'm going to go over a couple just housekeeping things, and we're going to talk a little bit about some of the metrics for the campaign so far, and from year 1 to year 2 to the present, and then also talk about this strange situation we're in globally right now, and how that affects some of the observations and measurements that we're doing. And we have a couple things that are postponed and canceled, and I'm going to show these in the next couple slides. So I see lots. So I also should mention there's lots of students online right now. So that's awesome, and thank you so much for the educators bringing their students on, because right now a lot of schools are out. Globally they're out, so we're doing a lot of distance learning. So this is perfect. This type of campaign is perfect, especially the webinars, because we do a lot of things online on this Zoom platform. So thank you to all the teachers who recommended this to their students. That's great. I see there's teachers on, there's students on. We have some scientists that are on as well, educators, at NASA and some other agencies. So, and universities. Thank you so much for joining the webinar today. So our campaign team, my name is Brian Campbell. I'm the lead for the campaign. And then on the campaign team, we have Dorian Janney. She's at NASA Goddard in Greenbelt, Maryland. Peter Nelson at Oregon State University, Christopher Schumann, Dr. Christopher Schumann at NASA Goddard Space Flight Center in the University of Maryland, Baltimore County, and Peter Falcon at the NASA Jet Propulsion Laboratory in California, where our speaker, Latha Bhaskaran, Dr. Latha Bhaskaran, will be presenting from today from California. So on the bottom, we also have the website URL to the Trees Around the Globe Student Research Campaign. And it's not too long a website, but that's where you go to get the information. And then you'll see on the left-hand sidebar, there's lots of information about the campaign, and you can learn all about it. All right, let's get into some of the metrics for the campaign, which I like to do every time. In year 1, we started the campaign September 15, 2018, and that first year ran a year through September 14, 2019. And in that time, we've had over 7,000 tree height measurements from almost 4,500 global sites. And we had just over 7,200 land cover measurements from 5,364 global sites, and 6,323 green up, green down measurements from 406 global sites. And the majority of those come from our friends at the European Phenology Campaign, which some of you I see are on here from that campaign. So that's excellent. And I'm also going to mention that next month, we're going to have a student extravaganza where we're going to have some students who are participating in the phenology campaign and protocol observations in Europe. They're going to be presenting at next month's webinar for the campaign. Year 2, which we're currently in, so I did it September 15, 2019 through today, March 17th, 2020. And we've had almost 7,000 tree height observations, 2,988 land cover measurements, and 2,628 green up, green down measurements. So the numbers are growing all the time. For the full campaign, you can see here, we have just over 14,000 tree height measurements, over 10,000 land cover measurements, and 8,951 green up, green down measurements. Now, we've also had 18 webinars, and we have lots of participants from 44 countries. We have lots of blogs that people are viewing, and we have lots of documents you can get on the campaign site. What I want to mention here is that we're giving you these numbers because these numbers represent data points that anybody, students, teachers, citizen scientists, professional researchers can use this data. They can look at this data, use this data, and use this for lots of different things, for research projects, to creating science posters, to just, you know, talking science with their friends and family, you know, because there's lots of great measurements up there, and you can, and I'll show you a little bit where you can access all that information if you don't know that already. I want to do a quick screen grab from the Globe website. This is showing you where all the tree photos, and these are from the NASA Globe Observer Trees tool, the citizen science app that we've designed. These are all the photos coming in from February 2020. And I just want to point one thing out. You can see that one to the north of Siberia, okay? Now that one there is actually erroneous because it comes from a school in Thailand. So something happened with the app. The app isn't always perfect, but when they did a tree observation in Thailand, for some reason, the latitude and longitude got thrown off a little bit, and it put it all the way up there at the northern tip of Siberia. I thought that was very interesting because when I actually clicked on the photo, there were palm trees in the photo. So as you know, there's probably no palm trees growing naturally in Siberia. It just won't work. So just wanted to let you know that sometimes we get the errors like that, but these are where they're all coming from in February 2020. Now, couple things going on. As you know, we're in a strange situation globally right now with lots of nasty things going on. So what we decided to do is we are postponing, not canceling, but we're just postponing the Trees Challenge 2020 for April. It's going to be scheduled at a later date because everything, we have to be really cautious of everything going on right now. So we just wanted to let you know that this is postponed, and as I mentioned, it's not canceled for good. We will be back at it. We're working on plans to do other things, you know, that people can do using distance learning. We're going to have things like some videos and some you know, resources that you can do during April since this challenge is being postponed. So I wanted to get that, you know, so you understand that that is not going to be taking place this April. Also, because of that, we had to also postpone the April tree height intensive observation period for April. Yeah, so that basically falls along the lines of, you know, we're canceling it because there's lots of you know, we don't want all this stuff happening. The whole social distancing thing is just, you know, a tricky situation right now. So we definitely want to make sure that everybody is safe and you know, and healthy. So we've done these postponed, and we're not going to be having this canceled. It will show up at a later date. So stay tuned. You know, I send out a lot of information. Our team does. So, you know, we'll let you know when it's, you know, back on the drawing board and ready to go. Now, with that said, next month, April 2020, we have our campaign webinar, and this will be Globe Student Tree Research Extravaganza. Students from around the globe share their amazing tree research. This will be on Tuesday, April 14th, 2020. And this will be 1:00 p.m. Eastern Daylight Time, which also comes out to 5:00 p.m. UTC or 7:00 p.m. CEST, okay? Central European Time. All right, so we're gonna be at the same location, same URL. So, you know, we'll hope you join us in. We're gonna have a bunch of students who are gonna be presenting on their tree research, tree and forest and phenology research during this webinar. So, you know, stay tuned, and it's going to be a lot of fun. All right. So just want to put a little disclaimer out here, you know, during our, you know, if you're out there taking observations and measurements, okay, we're not recommending that you go outside and do all these observations, but we know some people may. So we just want you to make sure that you are in this current uncertain global time, and regardless of where you are, please be safe and make sure to follow all local rules and regulations if you happen to take Globe protocol measurements and NASA Globe Observer observations. We want you to be safe. We want you to be healthy. We don't want you to do anything to jeopardize your health or anyone else's health out there. So I just wanted to give you this, and, you know, we have a global health crisis right now, and we just want you to all be safe when taking the observations. Now, what you can do, if you're, you know, in your house, you can go to the Globe database, and you can get here by going to globe.gov/globe-data, And you can go to the visualization site, like you just saw the picture of the globe photos. You can go there and take a look at the data. You can also go to the advanced data access tool where you can download a spreadsheet of that data as well. And you can, once again, look at all the data that's coming in from all over the world. You can put specific days in there to look at. You can go look at it, who collected what on your birthday. So, and this is globally. You know, we have 100 and I believe it's 124 countries now that are participating in the GLOBE program. So there's lots of data out there. And if you go back to the beginning of GLOBE in 1995, there's, you know, what is it now? 120 plus million observations and measurements since 1995. So there's lots of data to look at. I don't recommend you go look at all that data. That would be impossible. But take a look at, you know, some of the data of in your area as well anytime. Now, we are going to turn this over to today's featured presenter. This is Dr. Latha Bhaskaran. She is a geospatial scientist from the NASA Jet Propulsion Laboratory in Pasadena, California. She's going to be talking to you about the use of LIDAR to derive tree heights and other structural vegetation characteristics, applications for mapping habitats in a post-fire environment. So this is, you know, very important information if you want to know anything about trees. And this is what you're going to hear about. This is how scientists do their research, okay? She's going to present everything that she's been working on, you know, on this topic, and she's going to, you know, you're going to see just how cool this is and, you know, how involved this can be to get the best results possible. So I will turn it over to you, Dr. Bhaskaran.
Thank you, Brian. Can you see my screen?
Yes, looks great.
Okay. So good morning or good afternoon, or from whichever time zone you are in. I'm Latha Bhaskaran, and today I'll be talking about using LIDAR to derive tree height and other vegetation characteristics, and how we can use this information to improve our understanding of vegetation in a post-fire habitat. So to start with just a little bit about me. So I'm a geospatial scientist. I've been at the Jet Propulsion Laboratory, NASA Jet Propulsion Laboratory in California for a little over a year. And I've been working on post-fire mapping of vegetation using imaging spectrometer data. I've also been involved in several other projects, one of which is looking at methane emissions from the Arctic and boreal regions using imaging spectrometer data. So my background is in geography, and prior to this, I was at the Oak Ridge National Laboratory for 15 years, working on bioenergy and other topics. So this is a brief outline of what I'll be talking about. So I'll start with explaining what LIDAR is and what we can learn from LIDAR. And then I'll focus in on the specific LIDAR metrics that are useful for characterizing vegetation and trees in general. And then I'll talk about how we used information derived from LIDAR in our case study in the Angeles National Forest. And I'll end with some of the significance of using LIDAR in our work and also other possible directions and applications. So to start with, LIDAR is what we call light detection and ranging, and is an active remote sensing technology. And what that means is this is different from passive remote sensing. Active remote sensing is where a sensor sends its own light source and then detects it back. So the LIDAR emits its laser beam and then it captures captures what is reflected from that. Whereas passive remote sensing is they sense the light reflected by a different source. For example, the light reflects the sun's energy. When we capture that, which most of the other remote sensing technology are, that's called passive remote sensing. So what this LIDAR does is it emits, as I mentioned, light beams, and then it reflects, it measures the time taken for the beams to bounce back. And using this information, it tries to generate a three-dimensional information about the natural or constructed features on the Earth's surface. And LIDAR can be in different platforms. You can have ground-based LIDAR, airborne LIDAR, and satellite-based LIDAR. And the focus of my work here is mainly airborne LIDAR, but I'll touch a little bit upon some satellite-based LIDAR technology. later on. And to give you some examples of various applications of LIDAR, in environmental science and ecology, of course, there is monitoring of vegetation health, and then carbon monitoring. Understanding the above ground biomass helps in understanding carbon dynamics in a forested or other systems, and then tracking deforestation and looking at land use changes and vegetation and so on. And LIDAR also has some applications in hydrology where we can look at the watershed, or there are some LIDAR applications related to bathymetry where, based on using a different type of LIDAR, we can map the sea bottom or the sea or a river bottom. And this type of LIDAR uses a different remote sensing signal from the usual vegetation related LIDAR. And there are also lots of application in transportation, urban planning, and so on. One interesting application which I hadn't really known before when I came across is a lot of the autonomous vehicles use LiDAR technology to kind of understand what is near them and what are the objects near them and help set the driving based on that. And LiDAR is also useful in oil and gas and mining and exploration, archaeology, and many, many more applications. So, and to delve a little bit more deeper into LiDAR, so what is LiDAR? So as I mentioned, I'll be focusing on airborne LiDAR. And airborne LiDAR, it sends laser pulses to the ground at the rate of about 50,000 to 200,000 pulses per second. And then it captures the intensity and the time it takes for these pulses to bounce back from features on the land. And using that information, basically using the intensity of the returns and also the precise location of the aircraft and the orientation of the aircraft, the system is able to generate a three-dimensional image of what is on the ground. And if you look at this slide, for example, the aircraft flies over these trees, and then so at different heights of the trees, different intensity lights are reflected back. And that's captured as these waveforms. And based on each point, which is returned at different time intervals, we generate what is called a point cloud is generated. And this is one of the important LiDAR data formats, a point cloud, which some typical formats is .las or LAZ files. And there are various software available to process these files and to visualize these LiDAR data sets. So, and some of the key attributes included in LiDAR point cloud data are the XYZ, or the longitude, latitude, and elevation. And as I mentioned, the intensity of the return signal, and then the strength of the return signal, and the return number, in the sense, are we looking at the signal, the first return, which is what is bounced back on the top of the canopy or the top of a building, or are we looking at the last return, which might be what is bounced back from the bottom of the ground, from the ground. Sorry, I think, okay, moving on. I may have skipped a slide. No, that's it. And some other information which is available from LiDAR is also the classifications. A lot of the LiDAR products come up with what they call classification, which will differentiate between what's a ground point and what's a non-ground point. And in some more detailed classifications, it would say whether the point we're looking at is a tree or a shrub or grass and so on. And I thought I'll share this visualization, which also gives a little bit more kind of a sense of how LiDAR over vegetation is and the level of detail with which we can get information. Since this is airborne data, you can even look at individual leaves and look at the vegetation structure and cover and generate a whole suite of useful metrics from this. And this is a visualization which is created by the NASA Scientific Visualization Studio. And there are many more useful and informative visualizations like this on that side. And so to talk a little bit more about the vegetation related metrics we derive from LiDAR, so we need to understand how the point cloud is. And as I mentioned, the point cloud has information about what is reflected from the top of the canopy and the bottom and the ground. So some of the metrics we derive from LIDAR are canopy height, canopy density, canopy cover, above ground biomass, and so on. And if you look at this image in the bottom left, you can see that the first return is approximately at the top of the canopy. And the second return will be somewhere in the middle of the tree or canopy, and which will reflect bounce off of the stems, the leaves, and so on. And the third return or later returns might be reflected off understory or the tree or the stem branches in the bottom. And the last return is reflected off the ground. So by computing the difference between the first return and the last return, we kind of get a sense of the canopy height. And this visual on the right-hand side, which is from a paper by Hansen et al., describes this in a little bit more detail, where we see the canopy height is the height of all the trees here, and the canopy cover gives us some information about the density of the leaves and how far the density goes in. Are we looking at a dense canopy on the top, or are we looking at a tree which is evenly spread from top to bottom? And is there any understory vegetation? So there's a whole suite of information that can be derived. And I thought this gives a little bit more information on how the data actually looks like when we open the file and look at it. So on the left here is the point cloud, which we call the digital surface model, which is whatever is captured by the aircraft or the LiDAR. And here you can see the terrain, the mountains, and there are some shrubs along the ridges. And you can also see some trees appear here. So this is the first level model. And then what we can do is we can split this into a digital terrain model and a canopy height model. The digital terrain model will remove all the above ground features and just show what the terrain looks like. And this is a useful product as well, as I'll mention a little bit later too, which will help us understand the terrain and so on. And then after we remove the digital terrain, what we're left with is just what is above the ground. And we can plot that on a flat surface, and it will look like something like this canopy height model below. And here in this example, you can see that you can identify different types of trees, some shrubs, and so on, and which will help us look at the whole huge stand in general and also individual trees. So from the information I just mentioned before, the point cloud, we can look at a cluster of trees and also individual trees. We can look at the stem volume, stem diameter, the foliage, the composition, the density of the leaves, and so on. And in some cases, this information is used to identify the species, and also it could be at a broad level, whether we're looking at a deciduous tree or an evergreen tree and so on. And the high resolution digital terrain model derived from this point cloud data is also very useful to identify stream channels and riparian vegetation. So given this brief background about LIDAR and possible vegetation metrics that can be derived from LIDAR, I'll move on to the next part of my presentation, which will be about the project I worked on in the Angeles National Forest. And this was a multi-agency project which had many goals, one of which was the post-fire vegetation recovery. This project also looked at habitat associations for birds with some of these tree species. And there were a number of collaborators, some of whom the names I've mentioned over here. So my specific focus will be how have the vegetation communities changed post-fire in the Angeles National Forest. So we specifically looked at 3 fire scars in Southern California. And in this presentation, I'll be focusing my results on the Sayre fire scar. So if you're not familiar with this region, the Angeles National Forest in California is one of the biggest threats to this forest is wildfires. Every year there are a number of burns, and as time the number of burns is actually increasing. And so over the past few decades, the annual burns, in addition to the drought which happened here from 2011 to 2017, has greatly affected how vegetation communities have recovered post-fire. And so this affects restoration and revegetation efforts here. And it's important to understand how the vegetation was pre-fire and post-fire. So the goal of this project was to look at the pre and post-fire vegetation communities and map this. And one of the issues with this region is it's highly undulating terrain, and it's hard to get into all of these regions because of the terrain variation, and it's difficult to map that without any airborne or satellite-based information. So as I mentioned, I'll be focusing on the Sayre fire, and this region was burned in November 2008, which is about 5,500 acres. And this is in a mountainous region, so it's undulating terrain. And this region was previously chaparral vegetation, which is typical in this area, dry shrubs and so on. And after the fire, some of the post-fire concerns were like, are there going to be increased sediment because of erosion? And there was a concern that native vegetation, some of the native shrubs were being taken over by invasive grasses. And does this cause habitat loss for bird species? And also one of the big concerns for the Forest Service was how has the riparian vegetation recovered or doing, how is it doing post-fire? So to help address these issues, there was a suite of data sets we collected and looked at. And there was a team which went to the ground and collected a lot of field data in these square or rectangular plots in the study region. So this team went and calculated the vegetation type and the fraction of that vegetation within these plots, these approximately 50-meter plots. And this data helped us drive our approach or provide calibrate and validate our results, as you'll see later. And we also used imaging spectrometer, airborne imaging spectrometer data called AVERIS. And this is a hyperspectral airborne data with about 224 bands. So it's really high and has a high spatial resolution, about 5 meters since it's airborne. And various flights of AVERIS were flown in this region. And so we were able to get data pre-fire and post-fire, which was not the case in all regions. So pre-fire, we had a data set from June of 2008. And for post-fire analysis, we had data from 2014, 16, 18, and even 20, but we haven't analyzed, 19, which we haven't analyzed yet. So this hyperspectral data was pre-processed to remove effects from the topography and atmospheric effects and so on. We also removed some of the water bands to be able to identify the vegetation features. So in addition to these two data sets, we also used LIDAR-based canopy height. So we used LIDAR data from 2017 and 2016 for this analysis. The 2017 LIDAR was processed by my colleagues Antonio Ferraz and Fabian Schneider. And I processed 2016 LIDAR using data from USGS. So I downloaded the point cloud data and you process this in R to come up with the canopy heights. And usually while processing LIDAR data, one thing which we need to do is make sure we remove some of the errors and noisy data. There tends to be a lot of noise in some of these data sets. So we set thresholds like, for example, in this case, I set a threshold of considering only 99 percentile of the cloud points because the ones above that were probably erroneous captured in the sky or other data, other regions. And the digital terrain model derived from this LIDAR data was useful to look at the stream, the regions where the streams might be, and also some of the riparian vegetation. So when we started this work, our main goal was using AVERIS data and how are we going to come up with dominant plant communities. But then early on in this process, we realized that using just AVERIS, we could not distinguish some of the dominant plant communities. And there was a lot of errors and we could not separate them, even though we had good spectral libraries of what was on the ground. That's when we decided that LIDAR is going to be a useful, provide useful information here. So what we did was using the LIDAR data, we calculated the canopy height model, and we separated our AVERIS data set into what we call the riparian tree layer and upland layer. So the riparian tree layer is essentially all pixels with canopy height greater than 5 meters. So all of the trees which were taller than 5 meters were put in this group called this riparian tree layer, and all the other legions were called the upland layer. And so we ran this classification, which is called MESMA, for these two layers separately and then put them together. So this goes into a little bit more detail of our analysis. So the MESMA analysis, or the multiple Endmember spectral mixture analysis, takes into input spectral libraries of various trees and vegetation, and then tries to identify what is the dominant plant or vegetation community in each pixel. So this is processing intensive. So, and even with that intensive processing, it was hard to delineate just the vegetation communities with just the Everest data. So when we were able to split the Everest data into riparian and upland communities, we were able to get a much better classification. And just as an example, how our classification improved, here on the left is our classification before using the canopy height model. And here, if you focus on, it's not very clear, but the plots 91, 92, 93 on the upper, in the top part of the figure on the left. So those plots were classified as black sage and giant reed, which are mostly shrubs. However, in those plots, based on the ground data, which is described in the table on the right, you see that oaks are one of the dominant vegetation types over there. And that was so, even though we had oak spectral libraries in this classification, it could not capture that, it could not separate that. So after we separated Everest data into the riparian zone and upland zone, we used the same spectral libraries, but after separating them, we were able to get a much better classification. And so those same plots you see, the 91, 92, and 93 here have been classified as the oak community, which is the green color on the right in the image in the center. So it did greatly improve our classification. And this is just an image showing our final result for the Sayer fire boundary. And we came up with an overall accuracy of about 66%, which may not look like a lot, but in this scenario, at this resolution, this is a 5-meter resolution data set. And this result was pretty phenomenal and helped us proceed further on to look at prior years. So as I mentioned, the focus of our project was to look at the pre-fire and post-fire vegetation communities. And so using the same approach, the Everest and the LIDAR approach, we were able to classify the pre-fire and post-fire data sets. And here you can see pre-fire in the top left-hand side, and the other images show the post-fire communities. And just quickly, in the middle is the burn severity map. And as you can see that the regions in the middle were the ones which were most burnt, and there were lots of loss of vegetation. So which is captured in the figures on the images on the left-hand side. So pre-fire, the pinks and the greens, which indicate the shrub community 1, community 2. If you look at the image post-fire in 2014, they've been replaced mostly by annual grass. So there was a drastic reduction in the shrubs. But with time, the shrubs kind of came back, and this is also coincides with the time when the drought was waning off. And so in 2018, we saw a pretty good recovery of a lot of the shrub communities, if not to the same community type, but there was a lot of recovery from the annual grass communities. And the other aspect we also looked at in this here is looking at the riparian vegetation. So riparian vegetation was of interest to the Forest Service, and to get a better understanding of what the vegetation looked like in these riparian zones, we used the high resolution digital terrain model derived from LIDAR and looked at the vegetation just in a riparian zone. So a 50-meter buffer riparian zone captured about 75% of the trees in the region. So in this particular region, most of the trees were located in the riparian zones. And we saw the progression of vegetation within these riparian zones in this chart on the bottom right-hand side. And as you can see, in 2008, which is the blue, annual grass, which is the pre-fire, annual grass was low, but post-fire, you can see grass taking over and the riparian trees kind of reducing and oak communities going down. But in 2018, we saw a great reduction in the annual grass and an increase in riparian trees and the oak communities, which shows some of the recovery of the riparian vegetation. This provides some more of the same trends which we talked about. For example, the first one is we saw a drastic increase in annual grass post-fire, and then decreased in 2018. Similarly, the shrub communities decreased post-fire, but then it's been showing a good recovery. And the oak communities, again, a drastic reduction since the fire, but then it's been recovering in the recent times. So to kind of wrap up this example, the using LIDAR enhanced our ability to use the imaging spectrometer data in our study. Um, Specifically, we think this is because the imaging spectrometer is a hyperspectral data and it was great in understanding the chemical composition of the vegetation, whereas it lacked that structural information which was needed to separate some of these vegetation types. LIDAR, on the other hand, provided the structural composition like the tree height and the canopy cover and so on, which was useful to be able to enhance this imaging, the results we got from the imaging spectrometer data. And this is critical in mapping vegetation communities at such a high spatial resolution. And it helped us really understand this rugged and previously unmapped terrain. This helped us get access to some of the regions which we normally don't see and hard to access in person. And some of the other relevant applications in this particular area is the structural diversity metrics can be an indicators of ecosystem biodiversity and forest health. And as you may remember, previously I mentioned one of the other parts of this research was looking at birds and how the birds related to these vegetation types. And there are studies which have shown associating habitat of species of plant and animal species with structural vegetation characteristics. So that's another area which we could look into in the future. So I thought I would end up by saying that the methods developed here integrates data at multiple scales and at multiple sensors. And this approach is transferable to other regions. And there are lots of opportunities to scale up and use data from other sensors, other satellite-borne data, for example, JEDI, and also future satellite-borne hyperspectral data to put them together and make some meaningful results. And I thought I'll show this presentation about the JEDI satellite. And this short clip gives some very useful information, and it puts together some of the thoughts which I've talked about earlier in a very nice way. So we'll go ahead and play this. And
We often talk about the biomass of the forest. All that is how much do the trees weigh? You know their biomass, how much they weigh. Half of the biomass of the tree is carbon. My name is Ralph Devine. I'm the principal investigator of the JEDI mission, and I'm a professor of geographical sciences at the University of Maryland. And it's really critical that we understand what the current carbon content of forests is today. We need a good global map of where the carbon is. The reason we need that is because whenever we cut down trees, we're going to release carbon into the atmosphere, and we don't know how much carbon we're releasing. JEDI will tell us how tall the trees are. By knowing how tall they are, we will know how much they weigh. By knowing how much they weigh, we will know how much carbon is being lost into the atmosphere.
So JEDI weighs about 1,000 pounds and looks about like a refrigerator. It's a telescope that's about 80 centimeters in diameter. It's 3 laser ports. Shoots out 4 laser beams that are then dithered really quickly in between shots. So it makes one laser look like 2. So I'm the instrument scientist for JEDI, and that's sort of the translator between the engineering and the science. So Ralph and I, we've been working on JEDI for 20 years, trying to get this technology ready and the science ready so we can fly missions. It's been great to get to this point. Okay, so JEDI is a laser altimeter, so it's an active optical instrument. So we have lasers that emit pulses of light. They travel down to the Earth, they get reflected from the Earth, and then we receive the reflection. So we time how long it takes to get there, which allows us to measure the range to the surface. When the pulse of light hits the surface, it gets distorted and stretched out by any structure that's there.
It looks almost like an echocardiogram. It's a distorted Gaussian waveform, technically speaking, And where the amplitude of that waveform is bigger is where there's more canopy stuff. There's more leaves and branches at a particular height, and where the amplitude is smaller, there's less canopy material.
The overall goal of JEDI is to systematically, consistently sample the most vertical structure of the world's forest, so we can estimate from that structure the carbon content.
Really, one of the coolest things about JEDI is that we're going to get upwards of 10 billion estimates of how tall trees are. It's highly likely that trees on your block are going to be measured by JEDI, and you'll be able to see how tall they are. We simply do not know how tall trees are globally. But this is really, really exciting and really cool. You can take your kids down the block and say, hey, JEDI measured that tree.
So with that, I'll end my talk, and I just thought I'll put some of these useful resources to learn more about LIDAR and some sources of some sites to get more, to download LIDAR data and look at some more. So thank you.
Thank you so much for that presentation, Dr. Bhaskaran. There's been a lot of chat going on in the group chat, the Zoom group chat, and Peter Nelson has answered a lot of those questions. So specifically about, you know, looking at tree species using LIDAR and lots of other things. So there's lots of stuff in the chat there. So does anybody have any specific questions for Dr. Bhaskaran today? And if there's anything in the chat, Dr. Bhaskaran, if you want to look in there at some, you know, while Peter's talking, you can take a look at that. If there's anything you want to add to, feel free.
I have a question.
Sure.
Yep, question coming.
So I'm curious, the work, will it be transferable over to other places like Australia and the habitat that's been destroyed by their fires? Was there mapping done
Yes.
globally that has a background so that when something changes?
So this hasn't been done globally yet, but I believe that this approach is transferable to other regions. Critical for this is having these three kind of slices of information. One is having some ground truth data, and then some LIDAR data to characterize the structural composition, and then either an imaging spectrometer or some kind of other remote sensing data to capture the chemical composition of the vegetation. So which will give us an understanding of what type of vegetation is there. So with these three types of data sets, I think this approach is transferable to other regions. And of course, like the specifics will vary. For example, we used a threshold of 5 meters to separate what we call was the riparian trees and the other regions like the shrubs and grasses. This, of course, will not be the same for different regions. So there are some changes to be made, but I think it's transferable.
And is the goal of this to be able to restore an area after a fire, to change the timeline in which it takes, or to just follow the succession process?
So the goal of the Forest Service is usually they do have some restoration efforts and revegetation efforts too. So in most cases it's hard to go back to what it was before, but what they've been doing is identifying regions which could be brought back to better state from what it was before, and also to protect other regions which have the potential to be under fire in future. One interesting thing about the region we looked at is, so this fire happened in 2008, but about 60% of the same region was in a fire last year. So we're hoping to look at what causes this recurrence of fires, and are there factors we can control, and are there types of vegetation we can put in to prevent that in the future. That makes sense.
Yes, thank you so much.
Mm-hmm.
Okay, we have a couple other questions in the chat. One is from Dr. Mohammed Naveed Tahir. He said, can LIDAR data be used to classify the crop species?
I'm sorry, classify the what species?
Crop, C-R-O-P, crop species.
Crop species. I think it would depend on the type of crop, because based on the crop height, I know different crops like wheat will have a different crop height versus other smaller low-lying crops. So I would say it is possible, but I'm not specifically aware of the studies which have done this. But based on my understanding of LIDAR, I would say it is possible because even crops will show differences in their structural composition. So it should be possible to differentiate them to some level.
All right, thank you.
Mhm.
Another one is what satellites deliver LiDAR data. I put in the comments that, you know, we have ICESat-2, we have JEDI, we also have ICESat data from 2003 to 2009. And question for you, what resolution can we get from like ICESat-2 and JEDI that you have been using the LiDAR for the LiDAR data?
So JEDI data came in recently, and I haven't used that as I could be wrong here. I don't want to give a wrong answer, but
That's fine, yeah.
is it 25 meters? But I would have to double check that. So I apologize. I'm not sure about the resolution of that yet. I started looking at the data, but I didn't get much far into it.
Sure.
So we used airborne LiDAR, which had almost a 1 meter resolution in some cases for the digital terrain model. So it was very high resolution.
Yeah, and with ICESat-2, when you're talking about like a spatial footprint, it's anywhere, it's on average between 14 and 17 meter footprint on the ground. So yeah. And last question from Marcus. Marcus is in Switzerland, by the way. Can you set up tree height maps like you showed from California with satellite data?
With satellite LIDAR-based satellite data, you can,
Yes.
but the resolution is going to be much coarser. It's not going to be as detailed as the airborne LIDAR data. And I believe JEDI does produce a canopy height model output. I think it's a level 2 product from the level 2 product output.
Yes. And we also should mention that, and Peter Nelson mentioned this in the comments, that, you know, JEDI data only collects data across the mid-latitudes because it's on the International Space Station, so it can only hit those mid-latitudes.
Yes, yeah, I should, yeah.
All right.
Hey, Brian, this is Chris Schumann. Check with Tony Martino. I think the ICESat-2 footprint is slightly better than that. Last time I asked him, it was around 13 meters across.
Okay, good. Yeah, so that's like kind of like an ever-changing thing because it's been.
Well, yeah, they're
Yeah.
The pre-flight number, I think, is what you were giving, and they are slightly better than what they expected to be on orbit.
Excellent. Well, that's good to know. Good. So about 13. All right. Excellent. All right. Well, thank you, Dr. Bhaskaran, for that great presentation. And as mentioned, we will be waiting a couple days to get this up on the website. Thank you so much. And now I'm going to pass it over to Peter Nelson. He's going to talk to you about some great online tools and looking at tree height and land cover. I will pass it over to you, Peter, because you're going to say a lot more than I can possibly say right now. So thank you so much, Peter.
Let me unmute myself so I can actually show you guys. Thank you. I'm excited to follow up with this, and I wanted to show you a little bit of what I've been looking at here in Oregon. You know, and so we've talked a little bit about Globe Observer land cover and photos, and I wanted to highlight an area that I know burned recently, and I wanted to just kind of show you a little bit of how I put together and some ways that you can actually use the Open Altimetry website to possibly look at an area that you care about. In my case, I'm zooming into an area here in Oregon, in the United States on the western coast. And one thing that I did notice as I zoom in, there was an area that I went through and actually looked at because it had burned previously. And so when we talk about burned landscapes, what we're actually seeing on the ground is things like this. In this case, there was actually snow on the ground. And if I blow up this picture, we can actually see standing dead trees that are here as a result of this fire that happened in 2010. And what was really interesting is that, let me move that down, is that when I go to the Open Altimetry website, there happened to be an area here, just in that same area where I did those measurements, right in here, where you can actually see there was green trees that were out there, or green areas in the satellite imagery. But then there is this kind of brown area that has an interesting shape to it. And that is the fire that happened in 2010 on the northern side of Mount Hood. And Mount Hood is one of these big volcanoes that has about 7,000 feet elevation rise. And so using the Open Altimetry website, I went in and I used the Select Region tool and just drew a box over an area where we can see the LIDAR measurements that came up. And so what that did is it actually opened up the beams and the LIDAR measurements that we were just hearing about. And what was interesting for me when I was looking at this, when I look at the photon heights, so this is the reflected light, and here we're talking about green light. So it's important to think about vegetation reflect that green light. And that's one reason why we see it as green. And so our eyes are doing remote sensing like that. And so one thing that really popped out that I thought was interesting is we kind of have the shape of the mountain. And this is, if we notice, here's the very top of the mountain on the left-hand side of those signals. And that's actually the white ice-colored top of the glacier of the mountain here. And then as we go down, one of the things that's interesting to note is we have these photons that cluster around at this 2,500 elevation all the way across, while we have the slope of the mountain actually go down. And so we actually recorded clouds in this. It's the only explanation I can think of why there would be this cluster of clouds at this location and this location. Just so very, very interesting the way that not only are we able to measure the ground with LIDAR, with these laser beams, but we actually are getting something about the atmosphere. So I just thought that was really interesting. And at first, looking at this, I just kind of see some blue lines. But if I actually go in here and zoom in just by dragging this, all of a sudden I can actually see that point cloud that we were hearing about earlier. And I can zoom in a little bit more, and what we see is the surface model where we get a lot of strong returns coming back. But then you can also see the top of the trees. So those were the trees that I was actually just showing you here. We were actually getting the LIDAR returns from some of the standing dead trees and everything. So this is why it's important for you to go out and actually make some of these measurements on the ground, so we have that reference data to understand, is this really cloud or is it vegetation on the ground? And there was a great question about whether we can use this to identify different types of vegetation. And in fact, we can. In this area right here, at the top, we actually see where we have kind of an even height of trees there. And that's a great way that we can tell that these are all living or about the same size, where this big gap that we have less dense trees is an area that you can then go out and explore when we're not under a public health crisis. So I wanted to highlight this as a way of taking what we've been talking about and even being able to look at it yourself, because this is one of the first data sets that allows us to look at LIDAR data and compare it to your location globally. And so that was a little bit of my exploration. And so as a result of that, it really got me kind of thinking about the data that has been coming in across all of our projects. And since we don't actually have LIDAR data around the world, what we actually do have is high resolution satellite imagery or imagery. And so I've set up this project for us to explore together, to look at some of these locations. And so we'll include this and do a little bit more of detail about how we can use this high resolution imagery to actually go in and look at data together. And so there is this tool called Collect Earth Online. And this actually allows us to go in, and if you look up the GLOBE program, and we have this project called Globe Trees. And when you go to that, what will pop up is you can see where all of the data coming in is located. And since I'm actually showing this live, some of the menus aren't popping up. But you can actually start zooming in, and you can start to see where we start getting the data that's coming in from around the world. And so zooming in on some of the data that we've had, we can actually use this high resolution images to start understanding what we're seeing in these landscapes. And so you can actually see this area right up here that I was showing you. We will have some areas where I went out and made some measurements right in this location. And the point is, you know, we can actually see this and be able to compare our ground, this high resolution imagery to what we're actually seeing when we look at this from space. So we'll set up another webinar to actually describe how you can be part of describing some of these landscapes with the high resolution imagery, which really complements the laser measurements. Because using these two things together is how we take these point measurements that come across with the LIDAR data, but then use the optical data that gives us what we call wall-to-wall coverage to be able to create a global height map of vegetation, whether it be trees or whether it be tall shrubs. So since our webinar is coming to a close here, I don't want to go through and throw a whole nother tool at you, but just I wanted to let you know that we will be developing this so that since we can't go outside and make measurements, there's another way that we can actually go back and look at our data and even find errors like what Brian was highlighting earlier about palm trees in northern Siberia. So I look forward to following up and sharing this again with you guys and seeing how we can actually look at our data and do some quality analysis with it. But since we've been talking LIDAR today, it's really a good time to go and explore this open altimetry tool and see what kind of laser beams and laser measurements were made around your location. And then use the Globe Observer tool or use the Globe visualization tool to see what kind of trees have been measured and start thinking about where you might want to go make some measurements later on when we're not under a public health crisis. So I appreciate you guys learning all about LIDAR. It's a really neat way to start thinking about not just spatially where things are located, but structurally what's around us and starting to think about how tall the landscape is. So with that, I'm going to stop sharing my screen and turn it back over to Brian.
All right, thank you so much, Peter. Does anybody have any questions for Peter? I didn't see any specifically ones in the chat.
Peter, this is Chris Schumann. By the way, your Mount Hood example is a great one of the fact that these high mountain peaks can make their own weather, basically just by forcing moisture to condense near their peaks. They're frequently cloudy for exactly that reason.
Right, and Dr. Schumann, that is a great example of why it's important to not only do the ground measurements of what we're seeing on the ground, which sometimes satellites can't see because of clouds, but to also think about and make those measurements about the cloud type at the time that you're making those measurements, because it really could be important to help us validate why we're seeing some of the data show up in different altitudes in that way. So I was just quite struck at that opportunistic piece of, it wasn't completely cloud covered at that time. It was actually at various a continuous elevation. And if you're above the cloud or below the cloud, you might be seeing something very, very different.
And another thing that your example showed up is that the cloud patch near the peak was essentially too thick for the photons to penetrate, but the one farther downslope was thin enough that you actually got ground returns and cloud returns. It was not completely cloud.
Exactly.
So different kinds.
Exactly. Yeah, it's just really fascinating to use this LIDAR system to start thinking about all that we can measure. And it really is just reflected light. And so as a result of that, you know, what we've talked about with Landsat or MODIS or some of these other satellite systems that we've been using for 40 or 50 years, LIDAR really in this case is just focused on that green laser beam and the green light and how the landscape or atmosphere reflects that light. It's really wonderful. And there are some atmospheric scientists who are using other lasers to look at atmosphere and measure the depth of clouds and other characteristics like that. So exactly what we've been talking about today has a lot of applications because it's just measuring light.
All right, Peter, there's a question from Dr. Mohammed Naveed here. He says, have one simple question. Might not be exactly a simple question, but this is good. Have you established relationship between the satellite data with the ground data? And this is in your wheelhouse perfectly.
Yeah, so in this case, right now, with the new ISAT-2 data that is coming out, all of the data that is produced by NASA and is archived does have some error measurements associated with it, and accuracy in terms of how is that laser or are those measurements in this location or that location. And so there is a spatial accuracy that's associated with those products. And that's what what we call the calibration and validation teams that work with these satellites. They spent that first year really just trying to understand what the data is coming in and how accurate it is, which was one reason why it took us a little while to be able to start serving that data out to our team and being able to actually use it. But that's where there is an opportunity for all of us to look at the measurements that are coming from ISAT-2 and then compare it to the measurements that you're making on the ground. And this question about are they the same? Are we even measuring the same trees is a fundamental question that our team and our group with the Trees Around the Globe student research campaign want to contribute towards. And accuracy is a really important part of what we do in science, and we can quantify that error if we do it in a systematic way. So I'm really excited to start looking at some of this data and seeing what we can actually do with it.
Excellent. Yeah, what I'm about to do is to look at some of that data comparisons exactly, because I looked at open altimetry and I found that the ISAT-2 data with all the trillion photons that have come out of the satellite, hit the Earth surface and come back again to the satellite, there was one photon that hit, sorry, we have howling dogs in the background, but there was one photon that that hit in our backyard in the woods that we own as part of our property. And I went out yesterday and did some tree height observations using the Globe Observer. And I'm going to be doing some comparisons, take a look at the data on open altimetry and then looking at those comparisons. So just to see how, check out the accuracy between the two. And, the big question is, as Peter mentioned, did I take an observation of the same trees that the satellite photon data is coming, is showcasing? So to be determined is the answer to that. Yep. So, all right. So we are at 3:06 p.m. Eastern Daylight Time. So we will I'll be closing this webinar, and thank you all so much. Thank you to Dr. Bhaskaran, to Peter Nelson, and to everyone asking great questions, and to all the students and educators who were on today. It's great. When I went through everything on here, it looks like we had about 8 countries, people from 8 countries present, so that was excellent. And as a reminder, this will be, it's being recorded and it'll be archived in a few days on the campaign website, and stay tuned for an email once that is ready to go. So thank you all so much, and remember the next webinar is April, geez, I forgot already, April 14th. So go on to the webinar page on the website and you can check that out, and you'll see more of that on an email from me. So thank you all so much and take care.
You too, Brad.